Hey guys, welcome to my channel, Math for Teens. Today is a bit of a different style video. Basically, this video I'm gonna try and teach myself and you guys the fundamentals of neural networks, get behind the math of it, gradient descent, like forward propagation. It uses a lot of vectors, which is cool because that's what I'm doing in school right now. And then I'm also just going to be asking beginner style questions and hopefully explaining to you guys those answers that we're all desperately seeking. And finally, as a total beginner in Python, I'm going to try and just work around some of the code involved in building a neural network and see if we can actually create our own. Yeah, so it's kind of it's a long video. Maybe I'll divide it, I don't know. But for now, what is a neural network? A neural network is basically just a function approximator. And it's kind of just a massive function itself. Because what are you doing? Okay, what are you doing? So basically, you're feeding it some input. For example, a picture of your dog, a picture of text, a list of symptoms, right? Even just a number, x equals 5. Then, what do we do? Well, we have a few operations. Now we're going to multiply this input by what we call a weight. Well, sorry, before we get into that, what I've done is I've fed my neural network an input. Something happens. A lot of stuff happens, right? We've got weights, we've got biases, we've got activation functions, a whole lot of math. And at the end of it, what do we get? We get an output. Usually, like for example, a prediction, we could be predicting the temperature tomorrow, given today's temperature. We could be, diagnosing somebody, predicting what type of dog someone has, predicting a test score based on how many hours they studied and slept. So the applications are pretty, there's kind of an innumerable amount of applications, and that's why it's so revolutionary today. But this is kind of the fundamental idea behind a neural network, I guess, if we want to start from beginning. And now, I guess the rest of this, we're going to dedicate some time to just exploring what is happening actually inside of the neural network. And so I'm going to just tell you what happens, and then we can get into, why on earth does that make sense? So we started with our input. And what's going to happen is we're going to multiply it by a number, which we call a weight. So multiplying by weight gets you to a new number. Actually, let's just do the simplest form. Multiplying by weight gets you to a new number. And multiplying an input by weight, we say it gets us to a new neuron. So this was, let's get some stuff. Oh, not a heading. Actually, that's okay. So our input was here, right? That's what I discussed earlier. We call this green line, we call it a weight. It's a number we're multiplying our input by. And, this transformed input is called just a neuron. And to this neuron, we add a bias. Now, bias it's also just a number, except instead of multiplying a neuron, you are adding it to the neuron. Okay, so the neuron, I think, is technically defined, The neuron, I think, is probably technically defined only after you've added the bias, right? So times weight plus bias, and then, by the way, this is a really simple version, but yeah, after you have this neuron, is this our end is this our end guess necessarily? And the answer is no. So we could, what you often see is you multiply, hold up. What you often see is that people will multiply this neuron, all neurons, by activation functions. Now, this is because if you just look at what we've done here, it's just a linear function. We have y equals mx plus b, right? So, in other words, it's weight times input. Sorry, it's my table like shaking. Plus bias. This is just a linear function. And so a linear function on a graph, it looks like, a straight line. And we can create any straight line with this type of equation. We can choose its slope, and we can choose where it intersects the y-axis. So we can choose its y-intercept. And so if we just had to classify, if we were trying to learn a super simple function, I guess, what could do this? I mean, if we were just trying to, I guess, learn a linear function to begin with, right? If we're just trying to learn a linear function, I think that would this be all we need to do that? Because it can approximate, let's say, sorry, I'm trying to explain this correctly. Let's say that this is what we get. This is the line of approximations of our neural network. And what we're actually, wrong color. And so this is, for any x value, this is the approximation for it. The true values, let's say, are like, they're hovering around this line. So is this a decent, not accuration, anyways, is this a decent prediction? Probably this will do to give you a decent prediction on what your y value would be for a given x value. So let's verify this, I guess. I'm not an expert, so let's go ask Dr. Google. So what was it? If you have a neural network with one hidden layer, one thing I forgot to add is that, with one hidden layer, if you have a neural network that is basically just a linear function, nothing else, no activation, ignore what I'm saying, can it predict linear trends? Yes, so who can we give credit to for this answer? We have Adeline.ai, Medium, Scribd. I think it's Aaron Singh who wrote about this answer here. So yeah, if you have a neural network with only linear layers and no activation functions, it can predict linear trends. And I guess this is what mathematicians just call the linear regression model. Yeah, so we can fit any line to fit our data if it's just a linear, trend. Okay, so now here's what I want to highlight. What can this neural network that we've made, what can't it do? And the answer is, well, as it says here, this neural network here, it won't be able to predict curved, nonlinear trends. So when you want to be able to make predictions on, curved, nonlinear, complex trends, you have to you have to add what we call activation functions. Okay. But before we get into that, I don't know if this helps, but it's an interesting website. I think the credit goes to Daniel Smilkov and Shan Carter. Many people worked on it, Andrich Karpathy and Chris Ola. Yeah, basically they created this online tool to be able to visualize, I guess, how neural networks learn, I guess, maybe. I honestly am not too familiar with it, but this, can we change this somehow? What does this do? So, hold up, guys, let me just gather my thoughts. So, what do we have? I'm not really sure what the features part is doing, but this will be the output of a neuron. Honestly, I'm not too sure. Maybe this was a bad example to show you guys. But I guess I can just draw this out. If some of you know how exactly this website is helpful, please don't hesitate to comment down below. I would love to know, I guess. But, okay. So right now, I'm just gonna create a graph. So, as you can see, this can predict linear behavior. That's literally all we need. Basic neural network. Except, what if the information I'm trying to, not like comprehend, but the information I'm trying to predict, approximate, the function I'm trying to approximate is not a linear one. You know, what if it goes up and down? What if it looks like this? Now if I just use this neural network, which it just basically it can only the predictions it can make is just a line of predictions depending on the input you use. It could only ever predict I'm making a video. Oh, sorry. Okay. Let's say depending on the weight, right, m, the slope, and the bias, so the y-intercept, this neural network might only be able to give outputs that lie along this line. So clearly, a simple neural network like this is not going to be able to predict something like this. And so you might be wondering, well, let's just look at what neural networks normally look like. Well, they look something like this. This is from 3 Blue 1 Brown's video, I think. Hi, baby. Or something. Can I say no copyright if that helps? I don't know. We'll see though. This might be what you think of if you've seen neural networks before. These are your inputs. These are our weights. We're adding a bias to these neurons. And then we're multiplying by weights again, adding a bias, getting an output. And so what you see here is that what we have is just this part. Here they added another neuron. They multiplied this new neuron again by weight, and they added another bias. And I guess a few questions are, why would people want to do that? But I think that it comes more in handy once we get into activation functions. Could that actually help us approximate complex behavior like this? And now, what do you guys think? Because I think the answer is no. Because for us to be able to to approximate a function like this, we need to have a neural network that is non-linear. It can, except this neural network it follows the relationship y equals mx plus b. I need something else.
Sorry, you don't
I'm filming.
Oh, sorry. I was just gonna recommend to close the windows because it's gonna get cold.
Okay.
You already brought more up?
Yeah, I did. Okay, so basically, what do we have going on here? Yeah, we need to be able to predict nonlinear behavior. And so I need my neural network to no longer be functioning like y equals mx plus b. But if I just take this, this mx plus b that I've gotten, represents this new neuron, and then I decide, well, I'm just gonna delete part of that, yeah. And now I decide, well, with this new value, mx plus b, I'm going to multiply it again by weight, right? And then I'm going to get a new neuron. I'm going to add a bias to it, right? Will that help things at all? And then we can just copy paste this. Will that help things? And the answer is no, because here we just have a number. It just replaces x, and we're once again multiplying it by a weight, by m, and adding a bias. So it's never going up a degree. It's never becoming a second degree, third degree, fourth degree function, or anything really complicated. It will always only be able to predict linear behavior. No matter how many layers, we call these different layers of neurons, no matter how many layers you have. Okay, and so now that we know now that we know adding neurons is not the solution to our problem, I guess. Yeah, now that you know that's not the solution, actually, I want to talk about one more thing, actually, is because here I just did this path. Why are there neurons below it? And I also believe that it's just this neuron, it will be the sum of, neuron input 1 times weight 1, input 2 times weight 2, and input 3 times weight 3, all of that plus the bias. So all of these are going to be feeding a part of the inputs to this neuron. And so that may be why sometimes you see, the value of a weight is kind of a reflection of how important the associated input is to the end result of your function, or of your neural network. But here we're dealing with many inputs, and so it's a bit more complicated than the example we're dealing with, like right here. So next we have activation functions. What are they? Well, we established that as we have it right now, and even as you would have it here, you would only ever be able to approximate linear functions. And so I'd be hopeless for basically most actual functions neural network researchers try to approximate. So what do I need? Well, what I need is an activation function, and specifically a nonlinear activation function. And it's kind of like they sound. They're mathematical functions. Whoa, it's kind of big. They're mathematical functions that instead of going to this next layer, we would proceed to, hold up, finding it. Once we get a neuron, after multiplying by weight, adding a bias, we would proceed to multiply it, feed it into, wrong size. We would proceed to feed it into an activation function. I'll just put a, that does not look like an A, but an activation function. And what does this do? Well, an activation function, let's give some examples. Activation functions, neural networks. So, yeah, it adds nonlinearity into the network, which is basically, kind of what we just talked about. Some different activation functions are, I like the look of this. This is a video, who's it by? Well, it's a video on machine learning, deep learning, artificial neural network. maybe am I allowed to check out a YouTube video in a YouTube video? I don't know. I'll put this in the comment section for the description for those who want to check it out. It is made by Pankaj Kumar Porwal. So yeah, sorry for my pronunciation. And so some examples, we have a step function, which I guess we kind of learn in school. It's where a function like quickly jumps from one value to another. A segment function, which looks kind of similar to that. What else? I mean, a linear function is what we have. It's what we were kind of using before. A ReLU function, this I've used. So basically, if the value for ReLU, if this neuron has a negative value, I could have multiplied my input by a negative weight. Maybe my bias was negative. Maybe my input was negative. Who knows? But for some reason, this is negative. Once I apply ReLU to it, if it is negative, it will just become 0. So the new neuron will have a value of 0. And so it will only ever pass on 0 to all of the, well, no, that's not true, because you can add biases. But yeah, it kind of, it makes the neural network behave non-linearly, I guess. No longer just follows a straight line. We've added complexity. But we'll explore more of this once we actually get into using it. There's a segment function, the hyperbolic tan, and for me these all look really cool because having completed calculus 1, it seems like a fun occasion to use some cool looking functions, and we will have some differentiation going on in the actual learning process, so it's a good application for those of you who want to not only learn to make neural networks but also reinforce your calculus skills. Okay, so I want to come back here now, and now you can see we have an activation. Before I put it as linear, it's kind of reflecting what we had been doing. Let's say I put it as ReLU. I don't really know what exactly this setup is, but let's see. How do we do this? I don't really know what it... Oh goodness. Maybe we'll add some neurons. I wasn't even playing it before. Okay, this is interesting. What is this neural network trying to do? I think it's trying to maybe sort the blue and orange lines, potentially. Difficult to say. And I don't know if we need to understand this now, but as you can see, that this may be the line of approximations. At least from looking at it, it looks to be nonlinear. It can map a curved, division, I guess. But I think that this is actually a bit of more advanced concepts to do with state space, which we can get into, and I think we probably should at some point. Not right now. Okay. So for now, I think it's just good to know that you multiply a value by an activation function if you want to add nonlinearity. And it's because it quite literally will change the value of your neuron in a non-uniform way, so in a non-linear way. Okay, and then what? Okay, not the way. Yeah. I think that with this, is this enough to try and begin to code one? I don't know. I think, should we get into state phase neural networks? Because I'm not sure I get this yet. Let's go into AI mode, and I hope this is allowed on YouTube. We're going to take a picture of this and ask, what is this? What is happening here? Like, what is happening here? Is this approximating a line? What does this graphic represent? I'm trying to understand use of activation functions, help neural networks approximate non-linear functions. Okay. Okay. Yeah, so kind of like, I guess I was trying to say, even it's approximating, maybe it's approximating the boundary, I guess, between orange points and blue points, and it's curved, and it can actually understand this and approximate this. Okay, so let's be taught. So the network takes in 2 points, the horizontal and the vertical position. Sorry, it takes in points, which have a horizontal and vertical position. Except it uses their product as an input. Okay. The lines. So, sorry guys, just trying to learn. Maybe it approximates the boundary, and maybe after you code in, like, well, you've learned the boundary, you've been able to approximate it because you can learn non-linear things, and now does it say if something is above my boundary, like, you know, if y is, if, like, if a point is above my boundary, it is, you know, orange or blue or something like that, to then just have a reliable way to classify points depending on their position relative to the boundary. Above the boundary, okay. Okay. Yeah, so at the boundary, I guess you're in between orange and blue, so maybe the neural network is not good for that, is what it's saying, along the boundary. Okay, when a new data point lands on a grid, the network doesn't look at the picture, it runs the coordinate through its equations. If the resulting number is positive, if the number is negative, so what? Does that mean values on the border are 0? Are 0? How does that work? And there's something else I didn't quite understand that it was saying. Hold up. And is the output of the neural network, it's the coordinate of point, or the height of point, or is it its certainty of prediction? I guess this is complicated stuff, guys. So it's both, apparently. Okay, so they're asking us to imagine this was a mountain viewed from above. Now the output is the height, so okay, that makes sense. So for each, I guess, number you feed into the neural network, it will give you an altitude. So blue is a mountain. Positive numbers create a high blue plateau. Negative numbers are orange. And the white border is sea level, is what it's saying. Okay, so mountain, sea, plateau. Got you. Yeah, and height is relative to the border. So I guess, I mean, this makes sense. I guess the further you are from the border, I feel that probably means you have more certainty that you're a certain color, because at the border you probably have more overlap. Okay. But more on the logic, further points from border are higher certainty. I guess I'm really just getting Gemini to teach us, guys, sadly. We will get past this. Okay. Okay. I guess it's asking us to look at the S-curve of the tanh and saying that at 0, small fluctuations in your input can cause a really drastic change in your altitude, in your predicted altitude. So you're kind of it's less certain on the actual altitude because it's a bit more, I don't want to say chaotic, but sensitive. It changes quickly. So even a small difference, I don't want to say mistake, but like, how do I say this? I guess I will keep it at that for now. I know that's not a full sentence. But I think that we may be trying, I think that at this point it's a good idea to try and just make a basic neural network. And I think for neural networks, it's actually really helpful to learn by doing it, by making one, and not get stuck at the idea of having to learn everything all at once, master it all before you even start, because then you'll never start, right? So excuse me. Let's open Google Colab. Okay, so this is what I mean. I had some past experience. Not really, but a lot of these were just things I never continued. and things that Gemini helped me with. What I am going to do is I'm going to open one because hopefully it has some useful code because I forget, honestly, how to do this. So maybe it will help us to reread it over. And actually, this one was good. This one was good. Hold up. I have got in over my head. I've rushed this. We are not ready, guys. Oh my goodness. We still have the funnest part, which is calculus. Okay, so this entire process of multiplying your input by weight, adding a bias, and then doing an activation function, and repeat as many times as you want until you get an output. It's called feed forward. Basically, you're feeding your input through all of the parameters, we call the weights and biases parameters. You're feeding your input through them until you get an output. That is feed forward. So emphasis on repeat, right? You can do this pretty much as many times as you want. Maybe there's a downside of too many times, it takes too long to run. I don't really know. We're going to copy this, and then what is this? This is our feed forward. But that's not really learning, because I could put any weight and bias at random, and each time I would do it, I would get a different output. And who's to say that that output accurately predicts my function, right? So let's go back to our simpler case, this one over here. Well, okay, here I probably have an optimized neural network. It's predicting my actual real world outputs pretty well. But it's pretty unlikely that my first try, all my weights and biases will be perfect so that it predicts my actual data. Or, I don't know, I'm not saying this right, but oh well. Likely what will happen is I could get something like this. Like, no guy, I could get something like this. That is not predicting anything. And so this is where we really get into artificial intelligence, I guess. It's just the capacity, well, this is not a real definition, guys, this is just me speaking, but the capacity to actually learn, which is probably, I guess, a universal definition now that I'm thinking about it, but yeah, anybody can just compute things. But once I realize that my predictions are wrong, can I adjust them so that I can actually get to the correct predictions? And how is this done? I mean, there's many ways for a neural network to learn. And the way that I actually saw, like, a while ago when I was into this was, did I copy paste that? I don't know. Was gradient descent. So give me a minute, because this is, well, I think it's actually really interesting. If you guys want to take a minute and learn some calculus basics, chain rule is all you need, which is why I honestly don't understand why we're not doing this in school, because, I mean, way to get people into math. But anyways, oof. What do we have? Let's redraw this. Sorry guys, I know that this sound might be really annoying to you guys with my table. Basically, oh god, it's actually becoming annoying to me. So we have our input, and then what are we doing? We are multiplying this input by a weight. We are getting something else, and here, okay, it's okay, it's okay. Times weight, what? Times weight, plus bias. And then we have an activation function. Let's choose a different color. Let's go blue. Activation function. Oh, wow. Okay, we need to do something about this. Copy. Activation. Whoa. Okay. And then we end up with an output. Simple as that. Now I'm not sure that this will make any good predictions though. Like, this may not even have enough neurons to really do much, but we can get into that later with trial and error. I think that's probably the best way. For gradient descent, this is just learning the theory. So let's just add the last touches, right? This was my input. I probably should make these other different colors, but oh well. And this is my output. And okay, what if this is terrible? You know, like, what if it looks something like this? What do we do? How does my neural network learn? And so now we have to get into let's just draw a parabola. Because usually, well, okay, hold up. Let me restart, guys. The first thing to do is to define an error function. The error function, it's really important. So, what is the error function? Well, the error function, it's just a measure of how wrong the neural network is. So basically, if I had an input 5 and let's say the function I'm trying to approximate is, okay, let's get some writing going. Okay, so we're looking at the function I've been trying to approximate. Failing, but it's fine. F of x. F of x is equal to like 10x plus 6. That's what I'm trying to approximate. Excuse my bad drawing now. Right? Like, pretend that's 6. Oh wow, this is not working. Pretend that's 6. And then we'll just catapult upwards from here now, right? Like, I kind of regret choosing this function, but, kind of looks like a straight line at this point. But it's not, I promise. It's not. We'll just pretend that that's it. Right? Okay. So that's the function we're trying to approximate. Except the function that my neural network can predict, let's say, given my weight and my bias, is what it will predict. So what we'll predict is that it will predict g of x oh please, come on, give me a curve. G of x is equal to, 2x plus 4. And actually, for this neural network, we don't even need an activation function. We're just gonna cross that out for now because there's no need. We're only approximating a linear function right now, so it doesn't really come in handy. So without an activation function now, I can be certain that so this becomes my output. I can be certain that my weight is 2, my bias is 4, right? So for any x value, I would like g of x to match up with f of x. Clearly this will not be the case because they're totally different functions, but let's say x equals 3. What am I looking for? What is the real world value of y of f of x in this case? Well, 3 times 10, 30 plus 6, so 36. So we will get, what do we get? We will get f of x equals 36. 36. And what will g of x be? The short-term memory is pretty bad, guys. I think I gave 3. Yeah, I did. So 2 times 3, 6, plus 4, 10. So g of x gives 10. Now, that's a pretty big gap, right? Ooh. Sorry. And so, honestly, like, if you want to just calculate the difference between it's f of x minus g of x, so it's 8x plus 2, x is 3, so 24 plus 2, 8x, hold up. I swear I'm stupid. 8x plus 2, when x is 3, we have 24, plus 2, that's 26. What I was meaning to say like 20 seconds ago, but yeah, you can see the difference here is 26. Now, my predicted value is clearly not my real world value. I've clearly messed up somewhere with this neural network. I mean, clearly. My weights and biases are totally wrong. And so how do I get my neural network to fix this? Well, back again to the error function. And there's not a single error function. There's like a bunch of different error functions you could choose. The key idea, though, is that you do establish an error function that tells you how wrong your prediction is. And with this, you try and backtrack, redo your weights and biases to minimize your error function. So you're just going to tinker with your weights and biases until you've reached a minimum on your error function. So you could think of your error function like something like this, and I'm trying to reach minimal error. You might be like, well, can I just set the derivative to 0? Pray that it's a minimum, not a maximum. I mean, I could use the second derivative test, look for concavity. But can I just do that? And the answer is no. And honestly, I didn't really get into it that much before. So instead of gradient descent, why can't we just set derivative of loss function to 0? Okay, it is possible. I mean, yeah, given this function, it is possible, right? Because all we have is it's a really simple neural network, and we can use this in a second. But for most models, this doesn't work. I guess, okay, so let's just look at what it's saying. It's saying that the equations you'd get when you set the derivative to 0, you can't solve, I guess. So you might need an iterative method, like Newton's method, for example. to solve it anyway, which neural network in itself is just an iterative process, like gradient descent. Okay. Yeah, this was the other thing. Maybe when we set our derivative to 0, we won't be finding a minimum, maybe we'll be finding a maximum. Maybe we have non-differentiable points. Yeah. Okay. Okay. So you guys probably understand that. Back to this. For this problem, though, I mean, do we want to? Like, I guess we could. We could do that. We'd have to define an error function first, though, because we have to differentiate our error function with respect to the input and then find, with respect to our weights and biases, and find the ones that minimize the actual error. We could do that. Do I know exactly how? Maybe, maybe not. But I think at this point I'm going to leave that for next video, depending. How much have we done? Not that much. But we're doing the learning part now, at least. I mean, what if our error function is literally just f of x minus g of x, right? So what if then our error is just, I guess, you know, how wrong it is. We already said it's 8x plus 2. Ugh. 8x plus 2. Except, what is this doing here? X is my, hold up, brain cells are slowing with a minute. Whew. X is my input. I'm not trying to choose an input where my neural network and my real world values are the closest. I'm trying to make a neural network which will minimize this error. So I need to be differentiating with respect to my weight and my bias. Okay, so what do I have? Well, the general form of my neural network, my prediction, is, once again, y equals mx plus b. I guess we can do an attempt at this. Let's hold up. Let me do some erasing. Yep. So what I will have is my error is f of x minus this, so I have 10x plus 6 plus 6 minus my prediction, which will be mx plus b. Okay, let me correctly assign my negatives. Alright. So we can have 10 minus m x plus 6 minus b. So I guess we can just say, you know, error is equal to this. And what do I want to do first? I want to find the best m value, maybe, so the best weight I can use. So I'll differentiate my error with respect to my weight. So dE over dm is just equal to minus x Yeah. Okay. DE, and then what else? If I have DE, DB, that's just -1. So this is not compelling me. We may have done something wrong here, to be honest. So should I check it out? For linear regression, how would I just use derivative to minimize loss function? Loss function is just difference between prediction and real life. Let's see what it says. Okay, so I guess our setup is just wrong to begin with. Okay. If you just use the raw difference, the positive and negative errors cancel each other out. This process is called the normal equation approach. And how do we do this? Is this just me going crazy? Or does this look kind of complicated? So, I'm gonna leave you guys with this for now. I promise you, I will be back. I'll try to improve my calculus skills over here, because clearly we've got some not great stuff so far. Yeah. I will give you guys one thing, though. I think the problem with this is that the error function does not just work with a single input. How wrong a single input scored. It is every single input you can give it, how wrong the sum of all of those outputs is, I believe. So you say how wrong was this plus how wrong was that plus how wrong was that. You measure the total error of the entire neural network, not just of one chance, encounter with a particular input. If that makes any sense. If I had followed this through, this would be how am I trying to say this? If I had followed this through, then, well, it's because I don't think that this, can be right as it is. It says that, the derivative of error with respect to m, I just said, minus x. You're setting error to 0, then you get x equals 0, and now suddenly it feels extremely confusing. Should I just, no, I can't just give up and close the call quite yet. Let's actually figure this out. Well, can I ask it again? But why can't I just use difference straight up between prediction and real life? What will happen? Because confusing things are happening right now, and I want to know if that is legitimate. The math breaks down. Okay, that seems to be what's happening. Maybe I'll just screenshot what I have and ask it, what is wrong with this? Why don't this work? Okay. Look at your derivative for the intercept b is -1. Yeah, if you try and set this to 0, it's impossible. -1 is not equal to 0 because I'm trying to set the derivative to 0 to find minimum. To find an equation that minimizes the error, an equation of b. Yeah. Okay, that was kind of lying right in front of me, but I guess there is also some issues here. Yeah, that doesn't help at all. This part also is kind of confusing because it's just saying the slope is 0 when the input is 0. Okay, yeah. So, okay. So now, I guess we have no choice but to use the square the error before taking the derivative. And then it will work. Should I ask why that will work? Okay, but why specifically squaring the error? Who came up with that? Because we're just trying to actually gain an understanding of what's happening, why it's happening, all that. So it's called the method of least squares. Oh, cool. Yeah, okay. But for, oh, I guess this is important. Yeah, so I guess that the bigger your error, even bigger penalty, so it penalizes big errors. So all your points will be relatively, hopefully, aligned once the model has learned. So I guess we can erase this. We've seen a few, mathematical breakdowns. And we will use what it has said with blind trust for now, and hopefully not later. Okay. Why did I just erase all that? That's not what I wanted to do. Yeah, that was the what is happening? Did I never write E? It's interesting. Okay, now we will erase from here. This was our error. And they're saying that we need the actual error function that we should be using we've seen that using just the pure difference, that does not work. Mathematical breakdown. We saw it, AI saw it, so that's out of the table. We'll use the square of the difference. Yeah, it makes sense. Making sure I'm saying it right. Okay, and now when we try and differentiate, well, once again, I'm trying to find the ideal weight and the ideal bias. So I'm going to differentiate first along the weight, then along the bias. I'll do it separately. So dE over dB, over dm. But once again, like I was saying before, the real error function is over all of our different inputs. This here is just going to create the perfect parameters for this specific point. And that might be too aligned for a single point that it misses the general trajectory of all the other points. We might not need to perfectly guess for 3 if on average we're guessing better for most of other points. If you guys get what I'm saying, here we're kind of just targeting for x equals 3. So one thing to keep in mind, so dE over dm, well, this is just power rule, right? Something squared, its derivative is 2 times that something. But then we're also going to have our inside derivative, right, with m, which again will just be minus x, but it's okay. So we have 2 times, I'm going to write this part in the long form, 10x plus 6 minus x minus b times minus x. That's the derivative of minus mx. Okay. And then now this is something we can set to 0. Oh, I have 1% left. Thank you for watching, guys. I will see you in the next video. Yeah, feel free to continue this on your own, and I'll resume it soon. Yeah. So, yeah, thanks for watching, like I just said. And just watch out for the next episode, because we'll just continue trying to understand AI.